Evening, good morning from whatever part of the world you are. So today we have with us Claudio, and he's a civil engineer with a master's in geotechnics by in FEUP in Portugal, and has over 12 years of experience in tunnel and geotechnical projects. And currently he resides in Madrid, where he is in charge of ground engineering and tunneling design team at AYESA, and he is part of many teams such as ITACUS, Portuguese Order of Engineers, and he's also certified as C Engineering by ICE, and he's currently leading the tunnel design for expansion of Porto Metro. Thank you, Claudio, for accepting to talk on our platform. Over to you.
Thank you so much, Rishi, also for inviting me, having me here.
I'll switch off the camera, so there might be not like afterwards. I'll just switch it on.
Okay, so I should go ahead, right? Present and start presentation. Okay, I'm gonna
You can start presenting.
put up the slides. Let me know when you can see them, please.
Yeah, it's
The audio is
visible
good.
now. Yeah.
Okay. Okay. So hi everyone. So also good morning and good evening, depending on where you are. As Rishi was saying, I'm Cláudio Cabral Diaz. I am currently based in Madrid, and I am the head of ground engineering and tunneling at AYESA. And today I'm going to be presenting on the Porto Metro new Rubi line and the design of the conventional tunnels in residual soils. Just before going to more details about the tunnel, this is a presentation that I already delivered earlier in the year for the World Tunnel Congress in Greece. And are the same slides, so it's based on a paper that we published together, both people from AYESA and also from Porto Metro. And before we start going into underground and start seeing the tunnel's design and elements that I'm sure that everyone here likes to discuss, because I guess we are all tunnel engineers or related to the tunneling works. I think it's important to first to show you what you actually have, above surface. So in the case of Porto, in case you have not visited yet, it's a very, very nice city with quite a lot of hills, as you can see here on the sides. So here is one of the famous bridge, Don Luis Bridge, that was used to cross the metro also around the year 2000, where the first expansion of the Porto Metro started. And it's a bit of detail, but when you go to Porto, people think that Porto is actually the entire city, but you have in this side of the river, this is the river Douro. It means of gold in Portuguese. And in this side you have Porto, but when you cross to the other side, you actually have another city that is called Vila Nova da Gaia. So throughout the presentation, I will refer to Gaia and Porto, and because this project actually has an expansion first in Porto, a bridge, and then also an expansion in the part of the Gaia side. And I think as tunnel engineers, and as Rishi was explaining, I'm also a member of the ITACUS, and at ITACUS we promote the use of underground solutions for developing our cities and making them not affecting what we have at the surface. So obviously, if you do a metro project at the surface, you're going to affect a lot this. In the case of the topography here, it will be quite complex. So by putting these rails and metro systems underground, you are protecting what you have at the surface. Can be monuments, can be, in this case, some of these parts is actually like world heritage, protected. And by having the tunnels, we can protect all of this. So I want to first give you an overview of the expansion itself, because it involves different parts and actually two cities, as I was mentioning to you. So the project starts in the north side. So this is the north side. As I said, this is the River Douro. it connects to the existing station Casa da Música. And then in here in dotted line, you have the first stretch of underground project, like the first tunnel. And this is about 700 meters connection. Then you have a new station in cut and cover. And then it goes to the surface on the top of the hill. There is a new bridge here. You're going to see in also a bit more detail in the video that I have for you. And then it crosses to the other side of this hill in this side. We are already in the other city. Remember that I mentioned to you that in this the south side of the river is Gaia. And then we go at the surface and we have different stations. So first we have one Arabida, that is also the name of this mountain here. Then it continues at the surface to Candal, then to Rotunda. It starts to go and to not be at grade, starts to go with already some a few meters of excavation, so in between walls in here. And then it needs to go underground again to go underneath a live railway here in the Vezas. And then from the Vezas to Soares dos Reis is the longest stretch of the tunnel, so it's about 1.1 kilometers here. And Soares dos Reis to Santo Ovidio, we have again tunnel, about 700 meters. So in total, we have 2.6 kilometers of tunnels. Remember, in the first part, Casa da Música to Campo Alegre is the first stretch of tunnel. And then we have two stretch from the Vezas, Soares dos Reis, and the Soares dos Reis to Santo Ovidio. And in between, we have a bridge and also at grade developments. So you see here some figures of the project. You have the 2.6 kilometers and around 3.7 kilometers at grade, including 7 new metro stations, of which 4 are underground. I didn't mention, but obviously it's going to be the Soares dos Reis, the Vezas, Campo Alegre, and Santo Ovidio, the ones that are in the part of the tunnels. 1 new bridge. That's not part of our contract. That was designed by another company. And the forecast and the what we have for this project, like it's expected that we have an increase in around 12 million journeys per year in 2029. And in order to promote sustainable transportation systems, it's expected that this project by the same year will remove almost like 5.8 million journeys in cars or private transport modes. So by having these metro systems, obviously we are making easier for the people, don't have to use their cars or like a private transport mode and using a public transportation mode. So you basically have a migration of people that needed to use the car because they didn't have a metro station nearby, and now they can use the metro system. And in terms of the development goals for the project, we have the mainly the 8, 9, and 11. That in the case of 8 is decent work and economic growth. So normally these metro systems, they lead to the economic growth of the nearby regions. The 9, that is industry, innovation, and infrastructure. And the 11, sustainable cities and communities. So obviously these metro systems, they lead to a more sustainable way of moving around, of commuting, and also lead to less people, losing lots of times in traffic jams and things like that. So that's why we are calling these sustainable cities and communities goal also, Matt. And now there is a video that I'm going to show you in more detail what the project will look like. I hope you can see the video. If you just confirm the video is
Yeah, the screen is visible.
And the video is also right. You can see the video,
Yes.
or is it frozen?
Yeah, it's visible. Video is visible.
Okay, thank you very much. So this is explaining the extension that I was describing to you. So going from the Porto side to Gaia, you have the same extension that I just described in more detail. This is what the existing rail stock looks like, and the connection to Casa da Música, the existing station, which by the way is also being upgraded currently to have a bigger building there. Then it goes to Campo Alegre, that is the first underground station that connects to university, to faculty's campus, and it will serve about 10,000 students. You see here, they are basically, this is in Portuguese, but they are describing the underground station connecting to the campus itself. So it's going to help the university to have the students coming and going and commuting from here. So from here it goes to the surface. So it's going to go to the surface, and you're going to see now the proposal for the new bridge. So this is a quite large span bridge. And something interesting also about this bridge is that it will not be used for cars. It will only be used for the metro and then for the people, or pedestrian, sorry, and the cycling bridge. So again, promoting more sustainable ways of commuting. And you see here that is a very large span. I think it's about 700 meters. Span is one of the widest sections of the River Douro to cross. You see that the one existing bridge that we have here, quite famous at the back, the span is much smaller. Then it's going to arrive at the other side. So from Campo Alegre, it's going to go to the other side. This is about 100 meters above the river level. And here it's going to connect to Arrábida, where there is a shopping center, a mall. So it's going to connect to the people who will be able to go from here. So I'm not sure if it's a very good idea, to connect one side, of the students with the other side of shopping. But anyways, this is what we have in both sides of the river. And then it goes at the surface, as I mentioned to you in this part. So all of the roads are going to be moved to accommodate now the metro line at the center of this avenue. And then the roads are going to be moved to the sides. These are like the very simple and quite standard solutions for when you have the surface metro stations in Porto. There's a lot of granite, for example, and the rocks and the glass for those stations. Then it starts to go, and no longer at grade, starts to go deeper, about I think 10 meters deep, but still like not in a tunnel. And this is called the Rotunda station. So it's because of the name in Portuguese, roundabout. There is a huge roundabout here around. So this is how it looks like now. And previously in the animation, you saw how it will look like when they build the station. From here, it will start to go again further lower, and starts to have to go in a tunnel when it reached the Vezas. So the Vezas is the existing rail station. And in order to be able to install the metro, obviously, we will not stop the train's operations. So what we will do is like go underground and use a box checking to build that part of the tunnel. And then we're going to have a station in the Vezas, go on the largest stretch of the tunnel. Now this is the second station in Gaia side in underground, Soares do Reis, also in cut and cover. This is typical like how they look like from inside, so a lot of granite that I told you. And it's quite standard, this architectural solution for Porto Metro stations. And then from this last station, it will go to, sorry, for this last stretch of the tunnel, it will go to Santo Ovidio, that is the last station. And at Santo Ovidio, you actually see here, let me just stop the video. So you see the image that I showed at the beginning of the Don Luis bridge that showed the train crossing the river actually is located around here. And that metro line goes at the surface and continues throughout this avenue. So it will meet again that line here. This is called Santo Ovidio. And right now, the Portuguese government wants to build also the high-speed railway connecting Porto to Lisbon, the two Portuguese major cities. And they are planning to install one of the stations in here, so also in Santo Vídeo. Basically, going to connect different metro lines and also a future high-speed rail station. So this is how it looks like, the Santo Vídeo station. I see already like animation how it will look like when it's built. So continue now. Now going to really underground, as looking more into the ground itself. What we have in Porto is actually the Porto side has a geology that can be quite good. So a fresh granite that has some discontinuities, but the quality of these, the RKDs and the RMR, sorry, of this rock is really good. However, what happens is that due to the weathering process, it degrades into a residual soil that you can see, and it doesn't look so good. So for example, this is actually the residual soil of the granite. It goes more to a sandy material that doesn't have much cohesion, so is not stable enough. You have to use ground treatment at the face and things like that I'm going to show you in a bit. And in the Gaia side, we actually have another geology that are some schist materials. Is another type of rock, metamorphic, that when it degrades, when it's weathered, it goes more to a clayed material of very low parameters and stiffness that you see here. So it's also not very stable. So basically we have from very good rocks to very low quality soils throughout the project. That is quite challenging to go and build a conventional tunnel in such a complex and with so much variability throughout the tunnel. So I'm not sure if you are familiar with this kind of soils, but they are called like residual soils. So they are the soils that come from rocks, from weathered rocks. And the typical geotechnical sections that you can find are quite erratic. So they are not uniform at all. So you can have in some sections, due to the weathering, for example, you can have maybe some water ingress in some locations and water infiltration, and it will intensify the weathering of that rock in some locations, as you can see, for example, in here. Whereas other parts, you can have fresh rock. Imagine if you are building a tunnel in this direction, you can go from a very good quality rock to a ground that is not competent at all, and where you have problems with stability. These are the cores, for example, recovered from some boreholes in Porto. You see that you have the rock, granite, and then quite rapidly it just goes to a soil in a few meters. And also here you see the transitions of these materials. So even with the geophysics that we use a lot for this project, is quite difficult to capture very well where you have the transition between a good quality rock, and not because this is a more like let's say a smooth process of weathering. So how you actually tackle and design a tunnel in such a complex the situations that you cannot predict, where you're going to have some variations. So first, obviously we have a good GI to understand the different stretch. So here you see the three parts of the tunnels, the three stretch of the tunnel. So first from Casa da Música to Campo Alegre. And here you see the geotechnical units that we have classified for the project. As I mentioned, here in kind of like red, you have the granite. So the darker red is a good quality granite. So it's a class 1 or 2 granite that you can see here, almost no weathering in this. RMRs here are a bit on the, it can be even higher than this, but at least, it's competent enough. And then when it goes to a G5, it's a completely soil. It's no longer a rock. And you see that you have actually SPTs to classify them both in G4 and G5. So being G1 to G3, the rock part. And we have the same thing for the Gaia side. You see a lot of green now, and these are the schists in the Gaia side, being the X1 to X3, the competent rock, and then X4 and X5, the residual soil. Obviously, the number 5 in both scenarios is a very poor quality material that you're going to see that needs a lot of ground treatment in order to ensure stability and to reduce the displacements of the ground and at the surface. So here there is the concept of the space proofing also, and the cross section for the tunnel. This is, as I mentioned, a conventional tunnel. By conventional tunnel, I mean that is a mined tunnel, so it's excavated using excavators, and people there is not a TBM tunnel. A TBM tunnel would not be the ideal solution for this because the length is not long enough, and you have the Porto and the Gaia side separated by the surface and the bridge. So logistically, you will not fit the TBM to do this. So in the conventional tunnel, what we have, this quite typical system, you have a primary lining, that is the external one, that where we use sprayed concrete or shotcrete to build that primary lining when we are excavating. So you advance, you're gonna see the different typical sections in a bit also. You advance installing the primary lining, that is this one, as I'm mentioning here, the here part. So this is the primary lining all around. And then when you finish this to build the primary lining, we have a sheet membrane. So in between, so there is a membrane for the waterproofing that is installed in here. And then we have a cast in situ secondary lining, that is this one inside. That is the one that's going to take the water pressure in the long term. So these tunnels are completely watertight. So Porto Metro doesn't accept to affect the existing groundwater table. So they want a completely 360 degrees complete waterproofing system. And you see here this is obviously a double track tunnel. So you have the two directions, the two train directions in the same tunnel. It's not like two tunnels where you have one direction in each tunnel. And the section here is about 9.2 meters. So almost like, if you account for the excavation, is about 10 meters width by about 8 meters high. And this is just a particularity of everything that goes into the tunnel. Obviously, the tunnel itself is not just the civil works that we are describing in here and the tunneling works. Then you need also the signaling, you need also the MEP cabling, everything that makes then the tunnel itself to operate, the safety systems, communications, everything that goes here at the sides. And also, so here some maintenance and also emergency here, the route that you see at the side. So this platform that is created at both sides. And this is just a detail in here to show that wherever we have the curves, we have some curves, obviously, throughout the alignment. And in this case, I'm referring to the horizontal curves, the curves in plan. What happens is that we don't want to have an internal cross section that is different. So this cross section that you see here is the same throughout the entire tunnel. So in order to do that, we have actually sized the tunnel in a way that when you have the curves, what happens is that the center here of both between both rails, it just moves to the side. Okay, so in this case, you see that the center of the tunnel and the center of the rail, you see that is being moved to the right by a few centimeters in order then to get enough space to don't clash with any other elements. And by doing this, you don't need to have a different dimension, both for the straight part and the curved parts of the alignment. So this is quite typical. Is also done, in several projects, but just a detail. So now we go into more detail of the primary lining itself. Due to the different cross sections that we have encountered in our geotechnical sections, we decided to start studying this project by first creating around 30 Plaxis 2D models. So we create 30 typical sections that we divided in A, B, C, and D. You're gonna see these are types of also of supports that were created. And the geology here is like referring to both the granite and schist. So for each of these families of supports, we have the solution either for granite or schist, and this is basically depending on things like as the you see here the chainage of the tunnel. You see here the depth of the tunnel. You see here, for instance, the depth of the water. You see the sources that you have from the buildings and things like that. So change in geology, in depth, where taking into account, we create the number of cases that we thought were covering all the different design scenarios that we could encounter throughout the tunnel. We first start with 30 sections, and then we rationalize to around 20. And from those 20, we then rationalize to around 8 sections in Plaxis 3D. So first we start by doing some Plaxis 3D to calibrate the ground relaxation of the soil that's going to see. And in an iterative process, we work out then from the 2D to the 3D on many support solutions we needed. So obviously, the Plaxis 3D you see here will allow us to see things as the stability of the face, that it was quite critical for these tunnels in residual soils. It allows us things like as optimizing the ground treatment. For example, this is ground treatment using jet grouting horizontally. And you can see that we are concentrated the jet grouting at the center, because basically the extrusion of the face is more intense at the center. So if you can nail that center, you kind of like you are stopping the movements where they are more intense. And you see the perimeter, there is like actually arching effect also in this direction. I mean, the out of plane direction. So you don't need to treat so much next to the perimeter, obviously, because the perimeter itself is already blocking that displacement. However, the center is quite free to move. So you have to really make the center more stable. So we use different models. So in the case of the residual soil of granite, since we have sandy material, we decided to use jet grouting. They were modeled using volumetric elements. You see here jet grouting columns, both for the face and also for the crown here. And in the case of when we have the residual soil of schist, it's more like a clayed residual soil. So in here, we are using like fiberglass to the face, and we are using for polling to protect the crown. So all of these was checked both in Plaxis 3D. Then we had some Plaxis 2D for modeling, for example, the secondary lining, also taking into account the primary lining. So everything was designed using Plaxis 2D and 3D. And also we use some structural then models in SAP 2000 for junctions and things like that, where we have connections with the shafts. We don't, I will not describe the shafts in this presentation, but we also have 5 shafts throughout the contracts. And the kind of solutions that we came up for the sections are the support family A. So 4 types or four different solutions for the support A. This is obviously a section of a good quality rock. So you see here that the primary lining is almost like there is, I think, between 50 to 100 mil thickness primary lining. And the support here is mainly the rock bolts around. And you may be thinking why actually we have done the invert curved. That's because since they want the tunnel completely waterproof, there is no drainage for the soil. So in the end, we could not make an invert flat. Otherwise, the water pressure will be built up underneath the base slab and will be quite unstable. So we decided to do also an invert here curved, and then make it completely watertight, 360 degrees. And basically the A A1 to A4 are considering the different kind of families of discontinuities we're gonna meet throughout the tunnel. So in the case of the section A4, you see that we have less rock bolts. So obviously here the families of the continuities are more favorable. And in the A1 is the heaviest one. And then we also have A3, that is a particular one where we're going to go underneath basements that are very close. So the basement is maybe 1 meter here from these rock bolts. So we had to use shorter rock bolts to ensure we will not invade those basements, obviously. So this is the rock solution. Then the B is a support system that is used for transitions between rock and soils. So it's typically where you have the rock around here at the invert level, but from here to up, you already have a residual soil. So in this case, you need for the upper part, lattice girders and sprayed concrete. The reason why we are using lattice girders obviously is because of some of the boulders and things like that you can have an asymmetric loading. So that's why we in this project we decide to keep the lattice girders. In other projects, if it was like more London clay or things like that, we will not use them. But we thought that the risk of boulders and local instabilities require to use lattice girders throughout the contract. So in this case, you have the rock section at the bottom. So you have here the foundation for your lattice girders, and in the upper part, you have a solution of a soft tunnel, conventional tunnel, already with a liner of 250 millimeters, being split in 230 structural millimeters with lattice girders, and also sprayed, steel fibers. So there is no wire mesh. And then the 20 mil that goes to 250 is a regulating layer that doesn't have steel fibers, is to protect then to installation of the waterproofing. And the same in this case here. In this case, is a heavier solution, 330. Again, the 20 millimeters to achieve the 350 will be for the waterproofing protection. In the case of the support system C, this is a completely residual soil solution. So you see that is already top heading. So you see here the invert being excavated. So the upper part is top heading, and the bottom part is the invert. This is done with a round length of 1 meter. So we do typically top heading twice. So you do 1 meter, 1 meter, and then you come back and you do 2 meters of the invert, keeping a delay of about 2 meters to the face. But you are closing the ring quite close from the face. So this is a residual soil that is not the worst one. This is kind of like, let's say, a type 4 or a type 3. If you remember from the classification from 1 to 5, being 1 the rock and being 5 the worst. This is not a class 5. When we go to class 5, we have actually the heaviest solution. In the class 5, we have a quite thick primary lining. So we have about 350 mil primary lining, and we have also a partialization. So we do first a pilot tunnel with this geometry here. Is a elliptical pilot tunnel in order to see what ground you are finding, and also kind of like to use as a ground anchor at the face. So you are making the face more stable. It's almost like a huge ground anchor that you are excavating throughout the soil. Then we do top heading, followed by a very close invert, also ring closure. And in the case of this section, we have one where we have the invert, using wire mesh, another one for the worst material, that is the X5. We also have the lattice girders at the invert. Again, due to asymmetric loading, and the ground is very deformable. So these are the solutions. And also we have reduced the round length to 80 centimeters. So it's a quite heavy solution for the worst residual soil. And we have detached the ground treatment from the typical sections. So remember that in the beginning of the presentation, I was asking how you can design for accounting for, such a variability in your ground and things like that. So the answer is actually you can up to a certain level, but you cannot be 100% sure that you're going to meet that, geology that you are expecting from the ground investigation. Obviously, it's going to be slightly different. It's going to, or maybe quite different in some locations. So in our design, we have the typical sections that are not attached to the support the ground treatment, let's say. The ground treatment can be used regardless of the section, depending on some criteria that we have identified to be used at the face. Because maybe you have a rock in the bottom part, but you need to treat the crown with jet grouting. So even though you have a rock, it will be a type B, a transition. You need to use the crown jet grouting. And in the, as I said, like for the ground treatment, we use crown jet grouting for more like the granites and its residual soils. The forepoling for the schists and its residual soils, and then for again the granite, we use jet grouting for the face. And again for the schist, we use the for its residual soils, we use fiberglass doubles at the face. So this is like to show you then what is the different typical sections we have throughout the tunnel. Obviously, this is still design level. So this project is now being tendered for construction, and until the end of the year, there are two main GVs that have been have sent offers for this. So they're going to be selected. Obviously, we then going to have them building, and I'm sure that they will not have this distribution of support, because this is what we have in the design. This is the best we can get, and our best estimate for the different sections. So you see that the first section of the tunnel, that is the one in Porto, Casa da Música de Campo Alegre, is where we have mainly the type A support system, because we have mainly the granites of good quality. And you see the type D, that is the worst. We have very little in this part of the tunnel. When you go to the second stretch from the Vezas to Soares dos Reis, we have mainly this type C, that is actually a not so bad residual soil, and the type B, because there is a lot of transitions between rock and the soil. And the worst is actually the last stretch. Normally, when you have a problem, they kind of like intensify. The main reason here is because as you go towards the end of the tunnel in Santo Video, it is becoming shallower and shallower. So you are meeting worse ground conditions. That's why in this stretch we have mainly the type D. So this is in terms of the tunneling perspective, the most complex stretch to build. And here is like a total in terms of the distribution throughout the tunnel. You have actually a quite balanced difference of the different sections. These allow us to prepare for different scenarios that we're going to meet, and obviously they will have to adapt as they are excavating and meeting and seeing the ground and how it's behaving. But basically our design is flexible enough for them to adapt it as they are excavating. So just to get to the final considerations, conclusions, we believe that the use of conventional tunnels here, the use of the sprayed concrete liners, allow to provide flexibility, safety, and adaptability to the construction. That is what I was describing throughout the presentation. It was one of our main goals to improve the constructability and the flexibility of building these tunnels. The 9 typical sections were specifically taught to improve this construction and safety and quality. And then the use of the 2D models for the secondary linings allow it to optimize that secondary lining. We did some checks. In the end, they didn't go through because of procurement reasons, but we actually saw that the secondary lining could be built, the top crown, completely using steel fibers without rebars. But at the end, with procurement, that was not approved by Porto Metro, and they have a rebar currently being tendered. The use of the 3D models allow us to optimize, I believe, in about, I think our estimate shows about 30% reduction in ground improvements for the face compared with, analytical equations. by using the both in the same model, the ground improvement and also the structural liner. So you have everything in the same model, as it should be, but sometimes you don't have them. So in this case, we saw that the main thing was actually to control the center of the face, and concentrate our ground treatment there. And also the design workflow resulted in savings in both construction and costs and program, which support both the project objectives and the United Nations Sustainable Development Goals. So that is all for me. So thank you, and I'm open for questions.
Yeah. Thank you, Claudio, for an excellent presentation. So I have a couple of questions, but yeah, I'll just address to our attendees first. So we have a question from Abhinav, and he's asking, while traversing of metro through bridge, there would be discomfort or maybe safety issues to the people crossing parallel to the bridge through the pedestrian section, and what kind of measures have been adopted for the same?
You mean in terms of comfort or in terms of
Safety and comfort, I guess he's
the
asking about that.
safety? No, because both elements have been designed, to be completely stable and to do that transition for the people don't even realize. Maybe in terms of comfort, you have, um, to be honest, I don't know in detail, but maybe the comfort will be just people adjusting from going out a tunnel during the day, and then you have a brighter, day outside. I'm not sure if something was done to do that, if maybe there are some openings in the because the last bit is the a cut and cover, so maybe there are some openings, but I think naturally you will have some light entering also that part. It's not so much, for example, as in a road tunnel that you have, the drivers going from a dark environment to a very bright environment. Here you have the users, they're going to be inside the trains, and I don't think it's such a big concern, but maybe I'm wrong. I'm not entirely sure on that.
Yeah, and we have a question from him. The question is like, what type of ventilation system is adopted for tunnel crossing under the river?
Um, well,
Uh,
the here we don't cross under the river. We cross
Sorry,
above the river
for
because
tunnel crossing the river. Sorry.
uh, okay, the ventilation here is done via some shafts. So the shafts, they are the ones getting the air out, and the air is forced through the stations.
Okay.
And but that ventilation is mainly for emergency when you have fire. Okay, then in the stations you have some comfort ventilation provided for the station. In the tunnel itself, the ventilation is quite limited because it's only in the event of a fire you have to push that air, and the smoke
Yeah.
to make it safe.
So we have a question from Anshul sir. Sir, if you want, you can just say it out loud, sir.
Yeah, hi Claudio. Thank you very much for the presentation. Just one small doubt. Can you please elaborate more on the jet grouting method which you have proposed in one of the rock support system? Like what I can see is there were some localized jet columns. Can you please elaborate more on that?
Mhm. Yeah, they are columns of about half a meter diameter. So it's a technique called, like, in Portuguese called CCP. So they are like horizontal columns. Um, they are then I think is jet type 2, and they are then like you drill first a hole, a smaller hole, let's say 100 mil, and then you start to inject the jet grouting as we will do, but in horizontal fashion, not in the vertical one. Um, is something that we use a lot in Brazil also, and it was brought like the technology from Brazil. It's quite similar to a jet routing to that you will see, but it's not as this the I think the maximum they can do is a jet 2, not a jet 3, because obviously you have to control also the pressures to don't actually expand and move the ground up. The pressures are about 350 bars, so is jet grouting. I'm not sure if I answered or if you want to ask more specific things on the jet routing itself.
Yeah, like if you see the model, basically it indicates a localized columns, but like not forming any pattern. Like generally the idea is to probably reduce the stresses from the overburden. Like you put the way you put the umbrella, no. So ideally it could be in
Ah,
that manner. It is only on the face visible if you see the model. So that is a bit confusing. Like probably you can give more elaboration.
so the reason why we, okay, let's see if I understood correctly. The reason why we have them, let's say here, you don't see them, but they are in this direction longitudinally, right? They are, I think, about 12 meters long, okay, with overlap of 4 meters. And what they are doing is like they are nailing the face. So you are creating friction. So imagine the face is trying to move and evading your excavation, right? And what the jet routing is doing is confining it. Is almost like a pile in a way, no? It's confining it. When the ground is trying to move towards to invade your excavation, you have these very long jet routing columns that are holding it through friction. Therefore, you have less movements towards your excavation of the face, and therefore you ensure stability of the face. In other ways, if you don't put them, the face will collapse because there is not enough cohesion. And by controlling the movements, you are also minimizing displacements at the surface and impacts to other utilities.
Yeah, now it's more clear. I got just confused with the figure probably. So now it is basically meant for the face support during excavation.
Exactly. The same as the
Thank you.
fiberglass are used, in other
Yeah.
situations, but the fiberglass would not be good for a sandy material, because in a sandy material, you basically don't have cohesion. So you have a large displacement, and by using the columns, you can create large columns to control it. In the other situation with the schist and the clays, you don't need to use such a large elements because you already have some cohesion. So you need to control maybe using smaller elements.
Yeah, thank you.
Welcome.
So the next question, I think you have just answered it. It was regarding this dowels as well. So I think it is answered. And we have a question from Tanvi. So you can just go forward and ask your question.
Hello. My question was regarding what were the conditions that you faced when the tunnel went through a residential area? If there are any instances where foundation created obstructions, if any, then what were the methods used to tackle the situation? If the alignment was shifted or any strengthening was done to control the impact on these buildings?
Yeah. Bear in mind that it was not yet built, so it's being tenders. What we have is in the design, we have a number of measures to account for that. For example, in the situations where we have a rock, we reduce obviously the round lengths. Typically, with this rock quality, you could go with 2-3 meters round length easily. However, since you are so nearby buildings, you have to reduce that in order to reduce the vibrations with drill and blast for the rock. So in the terms of the rock, we reduce the round lengths to, and also use electronic detonators, for example. That's for the rock. We reduce also the length of the rock bolts to don't go um, to nearby those basements, as I was showing in the section A. And then in the case of the residual soil, that is actually the worst, that induce a lot of displacements. What we did is we use micropiles to strengthen some of the foundations of those buildings. And then we have a very, a monitoring specific for those buildings that is more complete. The the alignment itself was, yeah, it was adjusted to minimize, to have as much distance as possible from the buildings and everything. But the biggest problem to us was in the last part that you need to go and come again to the surface. So there is no solution there because you are forced to come to the surface and it goes shallower and shallower. So it was a requirement for the operation of the trains that it meet the surface at the end. So in there, what we have is like we strengthen wherever you can, and in some parts we had to go to the case of having to demolish the building because we don't have any distance at all. But that's like limited to 2 or 3 buildings in the end.
Yes, thank you.
You're welcome.
Okay, so anyone has more questions? We have another question from Abhineet. And is what support measures are adopted for tunnel passing through mixed ground conditions? I think support conditions B, as you had spoken in the
Yeah, again, it's we provide the both in jet grouting, fiberglass, and for polling, and then is we have identified the ground conditions. So in what we have is like we have all these scenarios. So you have 10 different geological units that we identify, and then in our design we recommend, for example, if you are in X5, for example, go and apply for polling and fiberglass. But then it's also up to the guys on site at the face to increase that. If they see, for example, maybe they think that they are in X3, but they start to see some issues, and locally they can actually install more ground treatment.
Okay. So yeah, I just had a question from my side. I just wanted to know how you came up with the pilot tunnel uh, concept for going further to see the ground. So how you decided the geometry or something? Can you just explain it in brief?
Sure. So the pilot tunnel looks like this. It was because this soil in particular has a K node that is very, very low. So meaning that the vertical loads have a big impact. And when we start to see that if we use, for example, a side drift, it doesn't help too much because you still have a lot of horizontally, it will not help you much. So we start seeing that we had two main aspects that um, drive the pilot tunnel solution. So one was the K node being very low, and the second was the face was moving a lot towards the excavation. So what we saw was like, in order to reduce the displacements to levels that are acceptable in Porto, we had to kind of like almost like create first a smaller tunnel that we do with a pilot tunnel. And the pilot tunnel has the benefit of, it's quite vertical. So the pressures that you have in the upper part are kind of like counterbalanced by a larger area. So being the K node very low, it helps to have the pilot tunnel. It helps, as you said, like to inspect what is the ground condition that you're going to meet. It helps, for example, if you have some water, to install some drains and drain ahead of the excavation. It was a bit iterative. We first try with a temporary invert. It was not helping because, as you imagine, the issue was like, even if you put the temporary invert and then demolish it, it's the same because the K node is so low that if you have a very large span, the pressure from above will kind of like ovalize your tunnel a lot. So we quickly decided to go to a side drift or a pilot, but the pilot allow us to control it from the center and remove the need of using the lattice girders. The pilot tunnel being circular, you can just use sprayed concrete with steel fiber, so it's easier then to demolish because it's a temporary tunnel that then you demolish.
Yeah. Thank you, Claudio, for this wonderful explanation and the presentation. And I think we don't have much questions for now. I think Tanvi, are you still having some questions? Oh, yeah, I think
No, sir. Yeah, thank you.
okay. So thank you, Claudio, for presenting on this wonderful uh, topic and taking time from your busy schedule. And And thank you all the audience for being present over here. And I'm sure that this is quite a good informative session that we had, and it will be used as a reference in for further studies as well. We'll be putting this on YouTube. So yeah, thank you, Claudio, for your presentation.
So from my side, also thank you a lot, Rishi, for inviting me, and to all the Indian Society Tunneling members for having me,
And
for coming. And I wish you a good evening there.
and you too have a good day ahead.